So as I said, this is Micro 84 decoding. This is really going to apply to the guys on the call, right? We're going to be involved with this shortly. This is a picture, and I actually pulled this picture. I have this unit right here. This is an M8402 on the right-hand side there, and you've got 2 output cards on it and 1 input card. These cards were capable of 8 inputs or 8 outputs. And the very far left, the M84, that's the actual brains, the PLC, programmable logic controller. On the left here with just a couple power inputs and a voltage selector. And the top left-hand corner is the Micro 84 programmer. So this is actually how you read the information out of the unit and write to it. The program pack plugs into the bottom of the unit. And it can be used to, you can write to the program pack. It's almost like an external memory, right? So we can write to that. We can, if we have a program pack and we need to swap out a PLC, there is a way to push a button on it and dump that logic into the PLC. So it typically would stay connected to the PLC in most cases, but you don't necessarily have to have it to run it. So this programmer on the top is what we're mainly going to be going over. It's what we'll use to decode the logic of the PLC. I found this quite interesting. This was one of the first pages of the manual itself, and this lays out, and this stands true almost to this day, right? Well, to this day, it stands true. So this is explaining what a programmable controller is divided into and how it kind of works. And you can see here that on the left-hand side, you've got the operator, which would be us, and then or the unit itself, the program operator. And here's the program pack. You've got a power supply, a processor, user memory inside there, and then you control your inputs and outputs to user control devices. These are going to be valves, pumps, contactors, things like that. And that stands true to today, right? And I found it interesting that they explained this out, because back in the early 80s, this was fairly new technology. A lot of things were done with what we call relay logic, where you have a bunch of relays that would basically be your ladders, right? So they would just wire it in a way that they would only allow the output to work if the relay was made true. Did you say something, Elvis?
I was just about to ask a question. Compared to newer PLCs, what are some like restrictions these have?
And we're gonna go over and for the first one, like we saw in that first picture right here, is the amount of I/O. And I'm gonna, in the next few slides, we'll go over the limitations, the specific limitations for these modules.
Okay.
So, and actually, it's the next slide. So, here's the rules for it. So the maximum number of discrete inputs and outputs combined cannot exceed 112. In today's standards, I don't know if there is a limitation. If there is, I don't know that limitation number. We have plants, terminals that we can add what you would call a RIO, right? So remote I/O onto one system PLC, and you can expand it up to whatever the PLC is rated to. Like an L36, for example, I can have up to, I think it's 42 nodes, which means 42 other RIOs can be connected to that. So it's only limited by the PLC limitations. And then yet again, if your program memory, if you have a big program that's very complicated, you're limited from a memory standpoint. But in the case of the Micro 84, we can have 112 combined inputs and outputs. 14 discrete modules, so that's this cards, can be installed in one system. 2 analog register input modules can be installed on the system, and 4 analog or register output modules. Now that's a big limitation compared to today, right? We don't have analog limitation. We use analog for most of our stuff, whereas this was, I shouldn't say it was mainly designed for discretes, but it was, in our case, that's all we're using is discretes in and outs. That's what we're using. This shows the wiring of those inputs and outputs. So if you look on the left-hand side here, you can see the input card. And what this picture is, what this is depicting is you have a neutral. This works the same now today, right? We have a reference voltage. So in this case, the reference voltage is a neutral. And you guys understand hot and neutral, like on your outlet. Um, one of your prongs is going to be the hot, quote unquote, which is going to be the 110 volts to 120, and then the other prong is going to be the neutral, so it's the other path. It's basically connected to ground at the end. So what this does is, if we're feeding us, this is depicting switches here. So when the switch is open and there's no reference to zero, right? You know, this hot is not coming in, that input will not be on. So as soon as that switch closes, we have on 120 and our reference voltage is zero. So it'll see it go high, basically, is what it's doing, right? So it sees that reference voltage. This is 0 volts. Once it sees 110 come in, it'll go high and your input will be made. Make sense so far?
Yeah, it does actually.
And now the output works in a similar fashion, except for we're actually sending that voltage out. And in this case, you can see we have our neutral here because we need to be able to run the card itself. And the other side of these are relays, motor starters, solenoids. That's what these icons represent. So on one side of them, let's say it's a relay light or a relay itself, or a solenoid, you need that neutral side to, just like you're plugging in a hair dryer, right? What happens is when we send an output, we're sending 110 to the other side of this device. So that'll basically, it's basically like plugging in a hair dryer, right? So if R is the hair dryer, you've got one prong connected, and as soon as the output sends the 120, then the hair dryer is going to turn on. This is how the module addressing works. And this is super important when decoding these things, because you have to understand where your I/O is laid out. And it's pretty straightforward. For instance, we'll start with the first one here. Our inputs, they start at 1001. Now we only have 8 inputs per card, right? So our first card here, 1001 to 1008, that's what we'll reference inside of the logic for those inputs. So starting from the top to the bottom, 1001 to 1008. Now in a newer PLC, you're going to have, local, and then your card number, and then the input starts at 0. In Allen Bradley, it doesn't start at 1, it starts at 0, but it starts with that card number and then the input number for that card. In this case, we're doing 1001 to 1008. Here, our outputs, they start at 0001. Okay. And you can see as you go down here through the processors, what it looks like when you lay it out different. A good example on the bottom of how that's working out is, let's look at these inputs. We're going 1001 to 1008, 1009 to 16, and then we throw an output card in there. Well, that first output card is where you start your first output reference number. So that's 001. We don't care that we're putting it in between another input. It doesn't make any difference. It's the first card that's an output, so it starts at 001. And we continue our inputs further down the line on the third input card. So we ended at 16, and now we're starting at 1017 to 1024. And you can see your output card follows in suit with the outputs. This is the LCD. This is a screenshot of the manual, what the LCD looks like, kind of with all the everything lit up on it. This we plug right into the bottom of the PLC itself. It's self-powered from the PLC. It just uses a little RJ45, like an Ethernet connection is what it looks like the cable is. It could be wired differently, but I have the cable for it to plug in, and it just powers right up. It'll visually allow us. This is what we'll be referencing, and it's literally about I would say 2 inches by 3.5 inches in size. So it's quite small, and it's we'll go over some pictures of the actual what it looks like in real life. This is going over our module addressing yet again and our internal addressing. The module addressing is going to give us our inputs and outputs, but within inside of the logic, we're going to have different reference numbers to reference different things inside of it. So the internal logic itself, right? So our coils, obviously, this is showing your coils here, our outputs that we can use, and it's based off the model number. We're using the M8402. It just holds double what the 01 does, but it shows your sequencers, which I don't believe we're going to have sequencers in here. These 4,000 registers can be used as sequencers, but they're used as timers a lot of the time. And numeric data, right? Your 4,000 registers are a lot of your numeric data. And then you have your output registers down here. And on the left, I just went over the inputs and outputs yet again, right? So inputs, depending on the model number, 1001 to 1064 and 001 to 64, which would make that, total number. Like I was going over, this is a handheld device. This is what it looks like, the full thing. It consists of 4 rows and 7 columns. In the top or center right here is where you're going to go over each node or element, right? There's different modes on this programmer, and this is something we really got to be careful about when we're using it. Now, by default, it goes to examine mode, which is where we just want to look at the information. You also have data entry mode, supervisory mode, and air mode. Now, the most I've messed with is examine, supervisory, and air. Air is a very common thing for me, frustratingly enough. Entering in something incorrectly, the unit will error out, give you an error code in the bottom left-hand corner, and basically tell you did something wrong, and it won't tell you what it is. It'll just say a generalized statement. And I have the error codes in the presentation that we can go over to. So when we're using this examine mode, we should be able to monitor the network power flow status of any node inside of it. It's also going to show us the status of any register or coil. So it'll light up on the LCD with what's true and what's not true. It'll also show us if a timer's running through, it'll show us what that time is at or what's left on it. All those things can be seen in examine mode. So it automatically enters examine mode after power up diagnosis, and the cursor is positioned on row 1, column 1 of network 1. And now we'll go over this again, but these networks, quote unquote, a network is a ladder to me, right? So in typical logic, you'll have different programs. They could be ladder, they could be structured text, they could be function block, but these are just more of like a ladder or a program. And the device can hold up to 16 networks, so 16 different ladders, and they work a little bit different. We'll go over the logic of how they work, but we'll have to go through each one, and on each node they have multiple elements. So enter mode is if we want to enter new information. That's basically by hitting enter. So that's another thing in this examine mode. If you hit enter on something, you can change it while you're in examine mode. So we don't want to be doing that. We don't want to be hitting that enter button. That enter button is not to be touched while we're decoding a PLC. And this goes for anywhere, right? If you ever touch one of these, you want to be very careful just to use the arrow keys. Supervisory mode allows us to enter and initiate supervisory commands. So this is where I think I have a little. I'll show you the page on that. Air mode. This is going to show you the diagnostic error, and there's a whole bunch of different error keys or error codes that we can look up and see. Depending on the error present, certain keys will be operational, and this is a very common one to hit if we have an error, is the reset key, or you hit shift and reset and it'll recover, because the LCD basically locks up in error mode. It doesn't allow you to monitor through anything anymore. So you almost have to, well, you don't almost have to, you have to reset it somehow. So to clear it out of that error or to get out of that error mode, you have to either hit reset or shift reset to get out of there.
Just for my understanding, these connect to the PLCs, correct? The P370 programmers?
Yeah, they connect directly to it with a little Ethernet cable.
Okay. The Micro 84 PLCs. Okay.
Yes, sir. Now, this is just kind of going over the different areas of the LCD itself, right? You have your reference data, your node and element, and your status. The reference data contains 3 separate displays: network, reference, and data. Network display, that's going to show us a 2-digit display, which is 9 or 18. For us, it'd be 18 different networks, which are, like I said, different programs or different ladders. So, and each PLC will have 18 of these, up to 18, that will be used per PLC. So we can scroll through these, and I'll go over the keys to scroll through them. So each network contain up to 28 logical elements. So on each network, we'll have 28 points where we'll have to go through when you're decoding this and document what is in that logical element. So that means that 504 logical element possibilities in each PLC. And this will have to be handwritten down and one by one. So 504 times 3, you've got 1,500 elements that you have to write down by hand. And they have to be correct, right? And I'll show you the nuances of how something could be construed as something else, or you're looking at a little tiny LCD, so it's going to be a very time-consuming process to do this, but it's necessary to be able to see the logic. The reference display, it's a 4-digit reference display. That's going to show you in the upper node of the element, or for the lower node of the element, the number or holding register. So that's that 4001, let's say for a timer, right? Or if it's the timer's seconds, it'll be in that reference display. So seconds or tenths of a second, that will be populated in the reference. The data display, that's going to show like our inputs or outputs, right? So, or the current numeric value of the timer, right? It can show different things. So depending on what logical element you're on, it's going to show different things. And it'll become a little more clear the further we get in here. This is the node element display. I got a little picture here on the right-hand side of what an element would look like. This is does anybody know what this top right-hand element is?
I might be wrong, but is it some kind of gate?
It's a normally closed contact.
Okay.
And it's still used to this day, right? And in Allen Bradley and in ladder logic, normally closed contact. And the bottom displays a coil with a vertical connector. You can see it at the end there. And we'll go over in more detail, but that's what a coil looks like inside of here. It doesn't look the same as it would in an Allen Bradley. And this just goes over where the power flow on the node display is at and where you can position the cursor. And that's on these 4 different rows right here, and then all the way across. The element display is going to show these elements that I've got pictured in the right-hand side here. It's also going to show your timers, and I have examples of basically everything we need. The status indications on this LCD, you can kind of see it in that picture over there, except you can see everything on right now. It's going to tell you what state you're in. So if you're just in examine mode or enter mode, if your comms are okay, or if you've hit the shift button, right? So shift is right there below the lower arrow, right there, the down arrow. And when we hit shift, we can do things like go into supervisory mode, shift or reset. Shift will also give us, your addition function or your minus function rather than the one. You can also see here in the bottom left, you've got a closed connector. You can make it an open connector when you hit the shift key. And then also your timers up here for on your 8 and 5 or your counter. So that shift key, that's what that does is these little other indicators up above here. When you hit shift, it'll allow you to use the functionality of the other information right there. Enter, I highlighted this yet again because when the enter push button is pressed, that data is displayed on the programmer as entered into the controller. So we don't want to be hitting enter. Enter is something that we don't want to hit even in examine mode. Examine just shows, what we're watching. It displays it, the element status. So there's a LED, right? And it shows when we have something true, when power is flowing through the logic element. This was kind of hard to picture. We can go over it in the field, but it'll just basically show a shorted rung is what it looks like on that little LCD when it's true. These are our logic element keys. So this is for entering our logic, different elements, and I went over some of them. There's your timers at a 1/10 of a second base. You see the 0.1, timer 1.0. That's your timer in seconds. Counters, addition, normally open contact, normally closed contact, coil, and then shift would be for latch coils. When the shift function is on, the shifted operation of a double function key will be performed when the shift function key is pressed. And you go ahead and press it. We've gone over this, right? So you can cancel it though by pushing any other key, so reference, network, or search. So we can cancel out that shift if we accidentally pushed it. Supervisory mode. Now these are the codes that you put in supervisory mode, and the ones that I've used quite a lot would be start controller. So that when we change things and we go ahead and start that controller, that's going to basically start the logic running, and you'll see the run light come on if you don't have an error. Clear memory is another one, which we don't want to push when we're decoding, but if you were to have to change something, it'll literally clear all the logic in there. So it's something you don't want to push unless you're working on a test bench like I was. And then you have dump memory. So you can this is what dumps it into that program pack. And then I just put a little star here because when we go into supervisory mode and then we select one of these codes, and I hit enter, it's going to show pop up CONF, so which is confirm. So it's basically asking you, are you sure you want to do the action that you've chosen? And you go ahead and hit it, and then it'll say done. This is our shift reset. So this is how you get back out of an error state. Reset shift or just the reset key, because the unit does error out on a regular basis for whatever reason. Maybe you push a button you're not supposed to, or enter something in you're not supposed to, or go too fast. This just kind of goes over what the effect of it is. So it's equivalent to a power up on the programmer. Full diagnostics are run, and the panel enters examine mode, and it starts you from the very first network on column 1, row 1, everything right in the top left-hand corner. So the network shift key, this is going to get us through our networks or programs, right? That will allow us to move from one network to the other. Like I said, we have up to, is it 16 or 18 per PLC. So that'll scroll from one network to the other. And you can also go backwards. If you press the network key while in shift mode, it'll go backwards to the previous network. Or you can just scroll through the 8 or 16 and go back around, either one. This is the search function. So if we want to search for a coil with, a specific reference number, like maybe it's referenced in one network and or in another network than what we're examining it in, this is a helpful tool to be able to find that single coil. So you can select that single node with that specified reference number. So this is an example down here. So we would push the search button. We're looking for output 7 in this case, and then hit search. And it's going to start from network 1, column 1, and proceed over, right? And it'll stop with the cursor node. The search stops in examine mode with a cursor on the node which has just been found. So it'll go through and find it. So if we're referencing a coil or even an input that's used in multiple networks, this is that function that would be out. Now we're going to be documenting, when you decode, you're going to be documenting each program, each network individually. So it shouldn't be an issue, but if maybe it exists somewhere and we don't think it exists somewhere else, we could search for it to say, to confirm that it doesn't exist anywhere else. The memory protect key lock switch, there is a key on the bottom. Mine is missing. It did not come with a key because it's from the 80s. So I had to open it up and manually override it. But there's a key that allows you to keep from making changes to the memory, and that's what we'll want to keep in mind. I think the key for some of them will be out on site, so we'll leave it in lock mode so that it doesn't write. It's kind of like a protection, so you could only look through it, and you won't be able to dump something you're not supposed to. It's a physical key. This goes over just kind of the panel itself, and it shows what can be displayed in the network reference data power flow. It just gives you kind of a informational basis of what's on that LCD and what will display depending on what mode you're in, which is important for when we're in network and on examine. It's going to display the current network number. The reference is going to display the reference number or the preset value, and then your data is going to show, what one is it, what output is it, what holding register, what's in that reference, and which is where we'll mostly be working, is in this examine mode. And I've mentioned this before, a network, right, is the ladder diagram program. So it is the ladder or the program, and there's up to 18 in each PLC. So let's get into the logic. Now, this is an example that was given inside of the manual of the logic itself. And this kind of we'll just go over. The micro 84 function is to solve the ladder logic networks. So this is part of a network. You can see it's kind of starts at, I guess, the first rung, and you've got 1, 2, 3, 4. So there is only 4 rungs per, right? So the various elements of a network, checking the state of each input element or contacts open or closed, and setting the status of the output coils. So the output coils are like your 4, 5, and 6. And it performs the scan of the network. It checks the status from the leftmost column of elements first, and then proceeds column by column to the right. So a column would be, where 4 is in a column, 6 is in a column, 4 and 5 are in a column, this counter is in a column, 5 and 6 are in a column, so on and so forth. So it scans from left to right, but it scans column by column from top to bottom. So the output of the first element can be used as an input to the second element. This figure shows that sequence. So what they're doing here, right, is we're watching, what is this again? 004? Anybody tell me what this element is?
That's an output.
It is an output, but what's the element type? On the very farmost left. That's a normally closed contact.
That's what you said. I just forgot. Yeah, normally closed contact.
Normally close contact. And our coil is in the top right-hand side. So what's happening, we'll just look at the first part of this rung here. So what's happening is we're energizing this timer. And on these timers, you have to have input 1 to start it, and input 2 also has to be true. So this normally close is going to be closed because the coil's not on in the initial scan of this, right? It's a 60-second timer. So in the beginning, let's say we just boot up the PLC, our timer accumulator will start going up because we're true on both of these inputs, 1 and 2. Once it hits 60 seconds, coil number 4 will fire, which in turn will basically turn this off because we're watching for, it's a normally closed contact. So we will open that part of it when it comes on rather than the opposite way. A normally open contact works opposite to that. So when that coil fires off, it'll basically reset this timer. That's what'll happen is when that 60 seconds times up and coil number 4 turns on, it'll in turn turn this one off and start that timer all over again. Okay? That's how that timer works. Now this is kind of going over how that logic works column by column. And this is a little bit more simple of a way to look at it. So it's possible to arrange the logic elements in such a way that the status of a coil can be used as a discrete input. So a discrete input, we're kind of using it maybe somewhere else in the ladder. We're watching this coil too, but further down. So we want to wait until it's this, it's done. So they put it further down in the ladder. But what's going to happen here, same thing. See how this timer has a normally closed contact on 3, and then they're tying a vertical connector into this other one. So it's going to be enabled all the time. It's very important to know where this second input comes from on these timers. So this timer will count up on a 1-second time base for 30 seconds. When that 30 seconds is finished, this coil will become true because that's the output of this timer, which in turn is going to turn this status on, right? So we'll be able to see this close. It'll become true. And then once this coil comes on, this timer then will start. Do you understand the timers, how they're working inside the logic? I'm guessing that's a yes. So this is within the manual. This is the programming pad, they call it. So this is what we're going to be documenting. We'll have, like I said, 18 per unit. And these are the different elements, spot by spot. This is what was provided in the manual. And quite frankly, I tried writing some elements down, but I found it cumbersome and hard to read. So I edited it and made a little bit different for us. So this is what it'll look like when decoding. I felt that the open boxes were easier to read because, for instance, you can see, somebody tell me what the first element is in box 1, line 1. What element type is that?
Normally open.
Normally open. And what input is it?
It's input 1.
Yes, perfect. So now if you look at line 2, 2, what do we got there?
It's
Actually,
still open, correct?
No, that's an input still. We're still on 1003, so that's input 3, but what kind of an element is that? It looks a little different than the others, doesn't it?
Yeah, it does. I don't remember.
So that is a normally open contact with a vertical connector. So that's the reason I opened up the boxes, is because this is what it actually looks like on the LCD. And it's important because what it actually means is that 1005 in row 3, column 3, this is actually kind of in the middle of them. Okay, it's actually in between them. That's kind of showing, and we'll go over some more logic, but that's what that's entailing is with those vertical connectors, even though you can't visually see it like you would in a normal program, that's what it's corresponding to is those vertical connectors wrap around that 1000, that input 5 right there. So that's what that's corresponding to. Now I have an example of a latch coil, and this is how we're going to draw it out so that it's readable for me to decode and translate into Allen Bradley. The other example I have is what a timer looks like, and this is what, when we go over that node on that row, this is what it'll look like. It'll show you the top part of it. It'll show you the time base, which is 1 second in this case, and it'll show you in the reference 30, which means 30 seconds. Now, if we bump down to the other one, when we look on the LCD, it'll show us the same time base, but it'll also show us the timer identifier or the reference number, which in this case, I just put the first reference, which is 4001. Now in row 1, column 3, that's just, what is that? What is row 1, column 3?
That would be a coil, if I'm not mistaken.
Yep. And it's an output. It's output 1, right? So as we go through each node or each network, and then we go through each instance on each row, we'll be writing these down as they're displayed in the LCD so that when we're done, we have a full picture on paper of what it looks like. After we have it on paper, then we'll have to translate it, because the complexity of these Goulds is that they don't work, which we went over a little bit last week, and we'll go over some more, but the ladders, you can have multiple rungs tied to each other in one ladder, which is not typical of an Allen Bradley. So you can run, you know, a lot more complex logic in a smaller space, and they did that for a memory standpoint. So there has to be some translation done. It doesn't translate directly over to Allen Bradley. I can't just write, you know, the rungs as they exist inside the Gould. We'll have to document them and then translate them into the logic that makes sense in an Allen Bradley. These are those different elements. And for Elvis and Cody, this is going to be extremely important that you understand the references and what they look like. I tried to take a picture of every instance. So this describes what they are and exactly how they look on a running program. You have your normally closed contact with vertical connector, normally open with vertical connector. And that's literally the only difference between these two, but they're significantly different in how the logic will work. So it's very important that this little down LED right here is documented. Same with your coils. This is a normal looking coil. I don't think I put a picture of a latch, but it'll just have an L in between, and it's not that complicated. And this is a coil with a vertical connector. Now we do have closed connectors, which, you know, could be used if we, you know, they need to move over the rung a certain amount of spaces to get to their coil or to their normally open. So those are important. The open connectors are what is default in there. So they'll just be, there's nothing there basically is what that means. So that's an empty spot. It was hard to take a picture, but this is what the timers look like. This is the top of a timer. A timer takes up 2 of these spots. In this top spot, you can see the timer with the upper brackets around it and the time base in there. And in the reference, you can see the seconds. So that's the reference in seconds. So there's 30 seconds on this timer. And if we move that cursor down, it's going to show us the data, which is how many seconds are in there. And this wasn't a running program, so it's kind of irrelevant. What's important is the reference number. So it's still going to show us this time base, and it's going to show us the reference. The reference is important so that we can discern them from one timer to another. This is just another screenshot of those reference numbers. Like I said before, we have our internal registers, discrete inputs, outputs, everything's here. It's just for use of reference and getting used to what is what. Now, this is how a timer works. There's 2 time rates provided. I've gone over that. You've got 1 second and 1/10 of a second. We can use them to create as many logic program timers as necessary. The timer content is not lost due to a power failure. So it's not, when you power fail, we don't lose those timer data points, like 30 seconds or the register itself. And this just shows the timer itself. So these timers don't work like a typical timer would in an Allen Bradley. That's why I was kind of going over it a little bit more. It's a little bit confusing because we have to have input 1 and our enable or our reset true for the timer to start counting. So the reset will, if we toggle that on and off, it'll reset the time. But if it's not on while our input's on, whatever it is we're referencing to start that timer, it's not going to start to count up, right? So that's kind of important. So sometimes they jump around it, and we might just have a vertical connector that goes down right in front of it to enable it all the time. Or you might want to have something that resets it, like a coil further down in the line. Output 1, that's going to be the normally open circuit. This is what's important on the output of the timer. So output 2 is important too. It's just the opposite of output 1. So it depends on how they use it in the logic. Now, from the programs that I've seen, usually it's used like we would use a standard timer. So that would be your done bit, right? So when a timer finishes, it's going to fire true to, let's say a coil or, it has to be some type of coil. The counters work in a very similar fashion. I don't believe we're going to have too many counters, but they work in a similar fashion, so I just put them on here. And they're going to be displayed the same way, right? So it's going to take up 2 spots. You're still going to have your enables, your inputs. It's all going to look the same, and you're still going to have a preset and accumulator with a register number. We can do arithmetic in these devices as well, which, yet again, I'm not saying that we will or won't, but I highly doubt that we're going to be doing much math inside these PLCs. They can only do addition and subtraction. I can't do multiplication. A few other things we didn't cover were latch coils. They're pretty straightforward. You're going to have a latch, and you'll have to have that same coil unlatched somewhere in the program. Don't foresee us seeing that, but we could. And then sequencers or drum programmers. I don't think we have a lot of sequential logic inside these PLCs. I don't know that, but if we come across it, we'll reference our manual and go through that if we need to. I just don't think it was used very much. These are the different error codes, and there's a bunch of them. And if you get yourself in a situation, you can use this reference to see what's going on. A typical one that I was getting a lot was the transfer of 65 of user logic between the program pack and the controller was not successful. I don't know if my program pack has just got an issue. I'm not really sure, but I did pop quite a few different errors while going through this thing and had to reset to clear it. It does give you a reference if you've got something wrong in the code. It just doesn't tell you specifically what's wrong. Kind of just a generalization that something's wrong. This is just more error codes, and there's a bunch of them. This one I did get. Coil reference numbers must be unique. That you can only use coils once within a network, right? So we're only going to have the outputs referenced to a coil once. That's it. And why would we only have one output reference? Well, if you're going through one network, it works the same in a new program. If you have one coil being fired from one piece of logic, you don't want to be firing it or turning it on or off from another program, right? So it doesn't even allow for that. It just allows you to run it based off of one network, and there's only one way it can turn on. Here's our program logic examples. We went over this a little bit last time, but this is a motor control seal circuit. And I kind of put like little tags up here for what would be typical of the field. So if you look at this wrong, let's say we have an LSH, which would be a high switch. So let's say once we make that high switch true, right? And we don't have the stop button pushed in because that's normally closed. So we don't have it pushed in. So that's going to be true. We don't have the ESD, or in this case, it would be fail safe. So the ESD would be true until, pushed. Then what will start this coil would be our start button. So that's corresponded here to input 2. So when they would push that start button, okay, it's going to latch in 1001 because it's this rung right here. This is your latch, your sealing circuit right here. So as soon as we hit that start button, that pump is going to run. And what'll turn that pump off, right, is based off of either the stop, the ESD, or the LSH. So any of those things can do it, but we don't have to hit the start button again. That's what'll seal it in. So let's say our high switch, we've cleared the sump level, and our high switch goes away. That'll kill the pump. Does that logic make sense?
Yes. Yes, I remember that from last time.
Okay. And I did reference, this is one of their examples. I did reference the code here. The next slide is a video of what it looks like in the PLC. And this is the keystrokes to get this simple logic inputted. So I feel bad for the people that had to actually program these from the start, because for this little bit of logic, these keystrokes are entered. And if you miss one button or don't push it hard enough or whatever, it's going to air out on you. So we'll watch the video here, and we can go back and watch it again. It should play. There's the coil. And I'm going backwards here to go down and show you. There's that coil. See how that looks, how it's in between? And we'll go back one more time here. So this is what I was talking about, those vertical connectors. It put this where it put it. And we'll watch the video again. So pay attention to where the vertical connectors are on the first rung. We're on 1 and 2. Scroll back to the first or the second ladder here, and you can see on the second space is where I put that in. So we had vertical connectors on 1 and we had vertical connectors on 2, and that's where they show it right there. Does that make sense how it's kind of laid out? It doesn't look the same as logic, right? This is why, decoding it's going to take a little bit of time.
Right.
We'll watch it one more time and then move to the next slide. You can see my little node moving over, a little blinky light there. And this is shown network 2, so that's the second program in the unit. And I'm just showing you here what an empty element looks like. Good enough?
Yes.
Okay. I go over timers again just because I think I struggled through this a little bit, but it's important, especially when we're decoding, to keep track of those vertical connectors or anything before, this enable is going to be very critical to how the system works. And this goes for the counters, the arithmetic, all those things have these enable secondary input. And in the case of the timers, which is going to be used the most, it has to have that enabled. So we need to know what's enabling that timer. We have to know. And in this case, they're just enabling it all the time, which is fine. It's just we need to know what's enabling it. These are the keystrokes to get this logic in here. I just kind of wanted to show you what it would take to build yet again another very short, not very complex rung. This is the conversion of the network. Now this is, I think this is the last slide here, but this is full circle. So hopefully it's big enough that you guys can see everything. But let's just start at the top left here of, this is a network that was drawn out on the drawings. It is one of the few that I have of the PLCs. I have four examples of PLC logic, 4 out of 54, right? So this is network 2 in the smallest PLC that they have. And this indicates 2 normally open contacts or inputs, 5 and 8. You have your coils 5 and 13. So we have to break this logic down piece by piece, and this is what it looks like in an Allen Bradley. Now I've put these little descriptors in here at the top so that we can follow the logic from the network to the PLC. Now I don't necessarily think I'll have to keep these in forever, but they are useful in referencing, because that tells me where it was at on the old PLC. And these descriptions are on the drawings, the tag names themselves. So the descriptor up there is just telling me the input of the old PLC. The tag name is what is on the drawing. So this is input 3000 amp 2 from HCP. The second input is 3000 amp 2 lock. So the first part of this logic we need to solve is we need to make sure that we turn these coils on when we have both of these true, right? So that's what I've done in this first rung, as I'm watching both those. So that's where I take my first step. I'm going to turn on my start close contact and my coolant on contact outputs when these two are true. That's the first part of logic I solve. The second part of the logic I solve is I'm watching for input 6 to be off, which you can see here. That's, we're watching this. This is a normally closed contact, and 1008 is normally closed contact. So this is the second part, and that's going to fire these 2 coils. So I'm just watching. I'm just doing the very first part of this ladder. We're not going on further yet. So that's how I fire these 2 coils. Now this third rung in my Allen Bradley, this shows input 009. Now this is in another network. So within the PLC, you can't see it here, but you can see the end result of it, which is output 17, which that PLC doesn't have 17 outputs. So they're using that output 17 reference coil as just an internal output, right? So this is what it looks like in another network. And you can see that down here on the bottom left on D, delta, you can see it's a normally closed contact that starts this timer, this 1 second timer of 6 seconds, and then it turns on 17. So that's what they're referencing here in this other network. And this is why it somewhat gets a little confusing, because you can't see till you move to the other network. So I've just included that timer in this program so that I can finish the logic out. The timer doesn't have to be in this program like we've gone over before. We could make a network 4 that just had these timers and these corresponding coils, which don't physically exist, but they internally exist. Everyone following so far?
Yeah.
Yes.
Okay. So then I'm going to start to solve the rest of my logic, which what I need to finish solving, because that's the final outputs, this 3000 amp A on and off, is I'm going to start solving the on logic, finish solving it out. And what I know that I need to have is I need to have coils 5 and 13 on, which it shows up here, right? But I also need to have that timer done before I turn on. So that's what this shows here is I don't necessarily need to watch these inputs because I know that if those inputs are on, these coils are on. So I'm just watching the coils. So I'm watching the coils, and I'm also watching for that timer to be done to turn on. So that's the next part of the solving of the on function. Now, on line B here, we need to finish that logic out. So yet again, I'm watching for coils 6 and 14, which are commanded or turned on from these normally closed inputs. I'm watching those coils to come on first, and then I'm still watching for 17, this on status HCP, and I'm watching for 7. So I've just put it in this rung so that it follows through the same thing. But this is what it looks like in an Allen Bradley, right? And when we separate it out rung by rung, because an Allen Bradley doesn't logically work in the way that a Gould works, right? And then our final piece of the logic is our off logic. And that, in that case, I'm watching, let's just start from the beginning on line D here. You have 1008 and 1007. You have these closed connectors. That's where they would use those to get over to the end of this coil. So I'm just watching for those two to turn off that unit, or I'm looking for that start close contact and the coolant on contact to be on with 1007. So you can see 1, 5, 13, 7. That's the other way that this rung works. So you see the difference between how the logic interacts, right?
Yes.
Okay. So that's